Welcome once again to my YouTube channel. I'm glad to have you here. We want to solve some questions on the way. So I have this one question 1990. It says the diagram below represents part of the wave motion in air. If the wave travels with a speed of, alright, to question one. Right, question one. Speed of 300 meters per second. Okay, we asked to calculate the frequency of the wave. Now the question now is, what formula relates the wave speed with the frequency? We know that it's V equal N lambda. The question is, what is the wavelength? We'll now go to the diagram and look at this wavelength. Can you tell me how many oscillations you can see here? Okay, let's count together. 1, 2, and a half. So we are having 2.5 wavelength, and the distance is 3 meters. Now the question is, this velocity, this speed equal frequency times wavelength. What we have here is just one wavelength, not 2.5 wavelengths. So all we just need to do is take away this 2.5. And how do we do that? We divide both sides by 2.5. So it means this, we cancel this. Lambda equal 3 divided by 5 over 2. 2 times 2, 4 plus 1, 5. So lambda, as the wavelength, equal 3 times 2 over 5 equal 6 over 5 meters. Now we now substitute the value there and then find frequency. So that's 300 equal F times 6 over 5. This will be 1 and cross multiply. So that 300 times 5 over 6 equal to my frequency. So 6 in itself, 1. 6 here, 5, and then this 0. So automatically my frequency equal 250 Hz. Alright, so that's the frequency for that question. Now let's go to the next question. The next question says, the distance between two successive crests of the water is 1 meter. Now the question is, what is the statement? Two successive crests. Two successive crests. Remember when we were defining wavelength, I told you that wavelength is the distance between two successive crests, or the distance to cover one complete oscillation or vibration. So now we're told that the distance between two successive crests of water is 1 meter. So it means that my lambda is 1 meter. Okay, let's continue. If a particle on the surface of the water makes two complete vertical oscillations in 1 second, what does this statement mean? To make a complete vertical oscillation in 1 second. Remember, frequency, and that's why I have to take time to explain each thing. Now, frequency is the number of oscillation that is made in 1 second. Now we're now told that it makes two complete vertical oscillation in 1 second. So it means that my frequency is 2 over 1 second, which is the same thing as just 2 hours. Now calculate the speed of the wave. Calculate the speed. So V equal F lambda equal 2 times 1 equal 2 meter per second. That's how to solve that question. Now to the next question. The diagram below illustrates a variation of the displacement y of a wave particle with time t. If the velocity of the wave is 250 meters per second, the velocity of the wave is 250. Velocity 250 meters per second. Okay. Let's continue. Calculate the distance between two successive particles which are in phase. Which are in phase. That is also alright. Now, what we relate this, we are V equal F lambda or V equal lambda over period. That wave speed equal frequency times wavelength, or wave speed equal wavelength divided by period. Now we're going to go to the question and to the diagram. What can you see? We can see the displacement, and we can see that the horizontal line is time. So it means we can find the period from this diagram. The question now is, what is the period? A period is the time taken to complete one oscillation, or one circle, or one vibration. Okay, we have various ways of solving it. This diagram has made it simple. So I'm going to show you the two methods because sometimes they might not give us the value at interval. Alright, so the first method is we're looking for period. And I told you that period is the time taken to complete one oscillation, one circle. Now, look at this. This and this makes one circle, right? And the time at this point is 0.2. So it means that my period is 0.02 seconds. Just simple as that. Now, most time, these values will not be given to us. Okay? So the diagram, I think the diagram is like this. Yeah, that's how the diagram is. Okay, so now we're going to look at the endpoints, which is 0.03, right? Let's count how many wavelengths do we have here? We have 1.5. So I'll write 1.5 wavelength equal the time is 0.03. But period is not the time taken to cover 1.5 wavelengths. It's the time taken to cover 1. So we're going to take this 1.5 by dividing both sides by 1.5, and this we can do lambda equals 0.03 divided by 3 over 2, which is 0.03 times 2 over 3. So 3 is 0.1 into the 0.01. 0.01 times 2 equals 0.02 seconds. Gives you. So it's the same thing. The time taking to cover one wavelength is 0.02. So I would prefer that you know this method, yes. But if you see a question like this, straightforward, just know that the answer is 0.02. Now to calculate the wavelength, I will substitute my value 250 equal 0.02. So it means lambda equal 250 times 0.02, yeah. So lambda equal, I'll shift this decimal point here. Let's try to add 0.2 times 25, you give me 5.0 meter. So that's all about that question. Let's go to the next question. Alright, like 1992, the diagram below shows a waveform in which energy is transferred from A to B in a time of 2.5 times 10 to the power minus 3 seconds. We're asked to calculate the frequency of the wave. Frequency, we don't know. Time, 2.5 times 10 to the power minus 3 seconds. Okay. Some people will be like, they don't use velocity or frequency times wavelength, right? But the issue now is we don't have the wave speed. We don't have the velocity. So how do we solve this question? This question is kind of tricky, but look at this. We're given 3 meter, we're giving this horizontal line as displacement. But right now, we don't know, we don't need that. The reason is, if you look very well, it told us that energy is transferred from A to B. And the time it took to transfer from A to B is 2.5 times 10 to the minus 3. Can we ask ourselves, how many wavelengths do we have here? That makes it 2.5. Let's count. 1, 2.5. So I'm going to write 2.5 wavelength. The time taken to transfer the energy from that complete wavelength is 2.5 times 10 to the power minus 3 seconds. From here, I can calculate my period, because period is the time taken to complete one oscillation, not 2.5 wavelengths. Okay, so this we go, and then I'm going to have this. Okay, and this 2.5 times 2.5 is 10 to the power minus 3 seconds. So the time taken to complete one wavelength is period. So period automatically is 10 to the power minus 3 seconds. We're not looking for period, we're looking for frequency. But we know that frequency is 1 over period, which will give me 1 over 10 to the power minus 3. So it means my frequency is 10 to the power of 3x. Which is the last question. The diagram below represents a transverse electromagnetic wave traveling with speed. Alright, so I'm going to write my speed 3.0 times 10 to the power of 8 meter per second. Alright, what is the frequency? I think we'll solve questions like this a lot of time. Let's say, what is the period? What's the period? Let's find the period. Okay. So the formula that relates is V equal lambda over period. Alright? I will give you, find the frequency as an assignment. Okay. So, okay, the only thing that is left now is we don't know the wavelength, but we can see a diagram showing us the wavelength. So let's go and count how many wavelengths do we have here. 1, 2, 3. So I'm going to write 3 wavelengths equal 0.3 meter. But I'm not looking for 3 wavelengths, I'm just looking for 1. So over 3, and that equals 0.1 meter. So I can now find my period, which is 3.0 times 10 to the power of 8 equal 0.1 over period. Okay, so it means my period equal 0.1, which is taken as 10 to the power of minus 1. Right? Yeah. So divided by 3.0 times 10 to the power of 8. Okay, so it means my period is equal to, let's see, 1/3 times 10 to the power of -9 seconds. Okay, so that's all about wavelength. Next video, I'll be talking about stationary wave. This is progressive wave. I'm talking about stationary wave. See you there.